Our logic engine just manipulates symbols. Logical symbols like these have specific meaning to the logic engine. But all the other symbols we use have no meaning to the logic engine itself. They derive meaning only by the claims we make, our premises, and the way we interpret logical results, the things that the engine proves. So it doesn't matter what symbols we use. All that actually does matter is that we use them consistently. Now remember that this is true of Boolean logic too. It doesn't matter what names we choose for our propositions. Predicate logic is no different, although it may at first seem different simply because we now need names for more things: predicates, functions, objects, and variables. Let's look at some simple predicate definitions. We'll define department to be true of any value x if and only if x is, in fact, a department. Notice that this definition is stated in a way that makes sense to us, people. Just as in the case of Boolean logic, the way we make the definition useful to our logical reasoning engine is to assert premises about departmenthood. So let's enter a few. We've got that billing is a department and HR is a department. Similarly, we can define the predicate employee, and we can enter some facts about employees. So we have employee of Lee and employee of Brett. We can also define predicates that assert relationships between and among objects. So let's define works and enter some facts about who works where. So Lee works in billing and Brett works in HR. And let's define one more predicate, people person. Now we can use these predicates to create premises that tell us useful things about workers in our various departments. So for example, we can assert that any employee who works in HR is a people person. And now we can use our logical reasoning engine to do something useful. We can conclude that Brett, by virtue of being an employee who works in HR, is a people person. Notice that we read out the conclusion using the same mapping between English and logic that we used to state our original definitions. Because we chose predicate names that made sense to us, it was actually easy for us to do that. But the logical engine itself doesn't care that we chose such sensible predicate names. So we could instead have written something like this. Castle of X is true if X is a department. So billing and HR are castles. Anteater is true if X is an employee. So Lee and Brett are anteaters. Infests of XY is true if X works in department Y. So Lee infests billing and Brett infests HR. And poison of X is true if X likes people. Now we assert a claim that anybody who's an anteater and infests HR is poisoned. So now we can say that a particular individual who's, say, an anteater and infests HR is poisoned, and thus we can conclude that Brett is poisoned. We don't even need to use strings of letters. Any symbols will do. Notice that the logic engine works in exactly the same way, and we can still read this out as Brett is a people person. But of course, we're much more likely to make mistakes if we use silly symbols like these. All of this may seem obvious. The thing that may be the hardest to understand is how to use variable names correctly and consistently. So let's look more closely at this. Here was our first definition. We use X as a variable. We can read this definition as, for any value of X, department of X is true if and only if X is actually a department. Now the scope of the variables that we use in definitions is an individual definition. So within this one definition in the box, we will have to substitute one value for X consistently in all places, in this case 2 of them, whenever we use X. Now we can write our second definition, employee. Again, the scope of any variables is that one definition. In other words, these 2 definitions are to be interpreted separately. That means that we can use the same variable name, remember it's just a symbol, as we've done here in reusing X. But of course, we could also use a different symbol, for example, Y. The key is that we have to use the same symbol consistently throughout each individual definition. Suppose that instead we'd tried to define employee like this. We've used X in one place and Y in another.
That's nonsense.
Right. We haven't said anything about the circumstances under which some value X is an employee. What we've said is something about some Y, but where would Y come from? It's not mentioned in employee of X. Now let's go back to defining employee correctly, and then we'll define our third predicate works, which is true in case some property holds of a pair of values. We'll call the first one X and the second one Y. But keep in mind that our use of X and Y here is just convenient. It's completely unconnected to our use of those same names in our first two definitions. So for example, we could have reversed the X and the Y in both parts of the definition. Or if it helps to think of it that way, we could even use the symbols object 1 and object 2 instead of X and Y. Now let's go back to using X and Y, just because that's what we generally do. It's easier. So we've defined works of XY to be true, just in case X works in department Y. But what if we'd written something slightly different? Now works XY is true, just in case Y, the second argument, works in X, the first argument. We've swapped X and Y in the second part of our definition. We've still got a legal definition, but if we use it, we must enter our fact in a way that's consistent with it. Suppose that we write our claims as we did when we had our first definition. So we write works Lee billing and works Brett HR.
That's nonsense. Billing doesn't work in Lee, and HR doesn't work in Brett.
Now we need to write works billing Lee and works HR Brett. Because we swapped the arguments in the definition, we must swap them whenever we use the definition. Let's consider one other possibility. Suppose that instead of using two different variables, X and Y, we use the same variable, say X, twice. This definition is almost certainly not what we want. It's not going to be very useful. Remember that the scope of an individual variable is an entire definition. And within that definition, we must substitute a single value for every instance of a given variable. So with this definition, works is only defined when its two arguments are the same. It is, for example, true if billing works in billing, highly unlikely. It's not even defined for works Brett HR. And for many reasons, we don't generally want to allow predicates that aren't defined for all the values in their domains. Now let's return to our correct example and complete it. We had a fourth definition, this one for the predicate people person. And we add a premise, a universally quantified statement about employees in the HR department. Notice that when we write quantified statements, we also have to make use of variables. Each quantifier introduces a new variable. We've used X. Again, it's okay that we've used a variable that we've used before. The scope of this variable is the quantified statement, so it doesn't conflict with anything outside it. Now, if this claim is true for all values of X, it has to be true of Brett. So if we substitute Brett for each occurrence of X, we can reason that if Brett is an employee, which we know, and if Brett works in HR, which we also know, then Brett is a people person. Notice that we didn't have to use X in our premise about employees who work in HR. We could have used Y, or anything else. The only thing that matters is that we use the same variable name consistently throughout the expression. Well, actually, there is one other important thing. If an expression exploits multiple nested quantifiers, each of them has to use a different name. Now let's just see what would happen if we had not used all our definitions and our premises consistently. This time we've swapped the definition of works. It's true if Y, the second argument, works in X, the first argument. So we had to rewrite the premises about it, and we have work billing Lee and works HR Brett. Now let's see if we can prove anything. Oops, we can't. Since we didn't change everything else we've asserted, we're stuck. We have no premises that assert works X HR for any value of X. So we can't use our claim that if X works in HR, then X is a people person. So remember, whether designing a database or writing specifications for a program or doing mathematics, the key to specifying predicates is simple. Choose them and use them consistently.
So how do we make sure to do that, particularly if we plan to add premises over time and if a whole team may be writing premises? Then, simply as a matter of good design, we should use some design rules. Rule number 1 is this: use mnemonic names. So use department to indicate that something is a department. Don't use castle. Rule number 2, when defining a predicate of 2 arguments, write it so that it reads like a sentence, with the first argument as the subject and the second argument as the object. So works of X and Y is true if X works in department Y. And choose a predicate name that makes it obvious which role each argument plays. So works in is actually a better choice than works. Here's another example of Rule 2. We could define the predicate mother of X and Y to be true if X is the mother of Y. But maybe it seems equally natural to say that it's true if X's mother is Y. We can solve this problem by changing the name of the predicate. We can change it to mother of. Now, the only natural reading is that X is the mother of Y. The bottom line is this: the names we use are just arbitrary symbols to our logic engine. It doesn't care what they are, but we'll get nonsense out if we don't define and use them consistently. So we should choose names that make it easy for us to do that.